I don't know. I don't think everybody would agree once the next exam comes up. Well, we got, first things first, everybody pay attention to the black date on the board, 15 of March 2019. That is the last day of school before spring break. Now, I'll tell you, you've been the best students ever right now. Okay, that's easy. No, that is the last day to turn in late work. Now, let me elaborate on that before everybody panics. As much as I would really enjoy being a hard nose about it and saying after that nothing else can be turned in, I won't accept it, blah, blah, blah. I don't have it in me to do that. Okay, so I'm not telling you that I won't accept anything after this date. What I'm telling you is that after this date, I'm going to take all of the late work that's been turned in and I'm going to get it graded over the spring break week. So I will assure you that if you turn it in by then, I will grade it and you'll get credit for it. If you turn in something after this date, I will still accept it. And I will not penalize you for being late. I will put it in a folder, and if I get a chance, I will grade it and you'll get credit for it. And if I don't get a chance, then it won't get graded and you won't get credit for it. So, if you wait until after this date to turn something in, you're taking your chances. All right? So, everybody understand? All right. Last two classes I tried to get around to talking about the Hall. Hall effect. If somebody reminds me at the end of the class, I'll go over that again. But not yet. Here you go. You can start it around. All right. The Hall effect. Anytime you have a charged particle moving in a magnetic field, that magnetic field is going to produce a force on that charged particle proportional to its velocity and perpendicular to its direction of travel. So, if you have say a flat rectangular conductor, and you've got an electric current flowing in it, and it's inside a magnetic field. Boy, doesn't this class get boring when I've got a lot of drawing to do? That particle moving through that magnetic field is going to experience a force, either up or down, depending on whether it's negative or positive. That means that there is going to be a potential difference, a potential gradient set up, because you're going to have more charge on one side than on the other. And what that means is that charge builds up, it's going to start producing an E field inside the conductor. And that E field will get bigger and bigger until it becomes equal and opposite the force exerted on those moving particles by the magnetic field. Once it becomes equal and opposite to the strength of the magnetic field, then the E field stops growing, the charged particles stop separating. But it sets up a potential difference across from one side to the other of that little flat conductor. This is called the Hall effect. named after some, I guess, Frenchman. Is his name in here somewhere? E.H. Hall. I don't know if he was French or not. Doesn't matter. It was back in the 1800s, I think, when he discovered this effect. And it is the one time that I can think of that it might be helpful to you to be able to calculate the drift velocity of electrons moving in an electrical current. Because it's the drift velocity that the magnetic field acts upon to produce the force. Okay? What's interesting about this is it can actually distinguish between positive hole flow and negative electron flow. And it was using this effect that they were able to confirm that, in fact, in a p-type semiconductor, the p-dope, positively doped semiconductor, that it is actually the holes that move that produce the net current flow. The Hall effect, when you make Hall probes and things like that, it can actually distinguish between positive flow and negative flow based on the direction of that potential. So, that's all we're going to talk about with the Hall effect, because I can't imagine any other time you would ever need to calculate a drift velocity. And frankly, if you want to use the Hall effect, you're just going to go down to the electronics store and you're going to buy a Gauss meter or a magnetometer with I guess magnetometer is something else, but you'll buy a Gauss meter with a Hall probe that you can stick in the magnetic field and it'll tell you the direction and strength of the magnetic field. But I did want you to know, at least be familiar with the Hall effect and understand its origins and how it works. So, now let's talk about solenoids and electromagnets. Now, here, by the way, before we go on, we're not going to go into it here because, well, again, it's just not that important, but there is a section here right before 27. It's in 20-6. There is a section here on the definition of the amp and the coulomb. And if you'll recall, earlier in the semester, I pointed out to you that when I was learning all of this, the coulomb was the fundamental unit of charge, and the amp was defined as so many coulombs per second of electrical charge flowing past a given point. And then they redefined it. And then they redefined it again. And so I'm not really sure what they define the amp as anymore. It's voltmeters per second squared or some nonsense, but it still works out to coulombs per second. So Ohm's law didn't change, and Pluto is still a planet, period. Not negotiable. There you go. That's that. That's the end of all of that discussion. Now let's talk about the magnetic field due to a long straight wire. We've looked at two phenomena so far. We've looked at a magnetic field that is produced by an electric charge moving, a current in a wire. And we looked at the right-hand rule of thumb. You point your thumb on your right hand in the direction that the current is moving, conventional flow, positive flow. Your fingers will curl in the direction of the magnetic field. Let's look at it a little more carefully. The magnetic field is mu sub naught over 2 pi times the current over the radius. So you got a wire. Oh, man. Got a wire. And it's got a current flowing in it. somewhere out here at a radius r, a magnetic field is produced. Put your thumb up, fingers curl that way. The magnetic field here is going into the board. Okay? And no matter which direction you point that R, no matter how you turn that wire as you go around it, that magnetic field is going to be pointing the same way. If you go way back there, it's that direction. If you come over here, it's this direction. You come up front here, it's that direction. And they're different lengths because one's further away, the other's closer. That's the only thing I'm showing there. Look at it from the top. That's your wire. And let's try to draw this carefully. There's your wire. That's the current coming at you in the wire. Over here, the magnetic field is pointing that way at that radius. Come out here, it's pointing that way. Come out here, it's pointing that way. Always orthogonal, always perpendicular to the radius. No matter where you go, it's pointing that way. So you end up with these circular magnetic field lines around that wire. Now that, of course, is for a long, straight wire. And the strength of that magnetic field is u sub naught over 2 pi. Yeah. Times the current divided by the radius, the distance. We've also talked about the force that a magnetic field exerts on a moving charge or a current in a wire. That was one of the first things we looked at. The force make sure I write it correctly. Yeah. Is the current times the magnetic field times the length of the wire that is being exerted on. And normally you would talk about force per unit length. These are two different formulas that describe two different things. And yes, they're both formulas that you will probably want written down on your index card. So let me repeat that. These are both formulas that you will want written on your index card. And you want to know which one means what. This is a magnetic field produced by a current in a long straight wire. This is the force exerted on that current in a fixed magnetic field. This is the magnetic field. This one involves the magnetic field that the current itself produces. This one involves a different magnetic field that the current is traveling through, not the one that it produces itself. Okay? So what happens when we have two wires, two long parallel wires running next to each other? If they both have current flowing, then they're both going to produce a magnetic field. And the magnetic field that each one of them produces is going to exert a force on the other one. Okay? How? Well, and then let's stop there and think about that for just a minute, because this can be a point of confusion for people. And in a couple of weeks, it's going to get confusing when we start talking about mutual induction and self-induction, because we're not always going to deal with long, straight wires. But as long as we're dealing with just with long, straight wires, how much will the magnetic field produced by the current in this wire, how much will it affect itself? What happens when R goes to 0? This becomes undefined. Okay? So basically, the magnetic field that the current in this wire is producing is being produced out here where the wire is not. Okay? You got a very strong magnetic field circling right around it, because R is very tiny and the B is very large. But the further you get away, the smaller that magnetic field gets. The weaker it gets. The shorter the vectors get. And I really do want to impress upon you, you need to think about these things as a vector field. B is inversely proportional to R. E fields, magnetic fields, these are vector fields. Gravity, I suppose you might treat it as a vector because it always points towards itself, to the center, but gravity you can just think of as strictly a gradient field, a potential field, a scalar field. Magnetic fields and electric fields, you need to think of them as vector fields. There's everywhere around here is a vector, a straight arrow pointing in one direction. And that direction changes all the way around it. But it's still a vector field. Which means that if there is a current flowing in this wire, the current flowing in this wire is producing a magnetic field over here that is going to exert a force on the current flowing in that second wire. Okay, now I'm trying to be careful how I phrase this, because I want you to understand this magnetic field is not producing a force on this wire. I say it's not. It might be if the wire is made out of iron. Okay, if you've got an iron wire, then a magnetic field will exert a force on it, whether it has current moving through it or not. But I've never seen an iron wire. Wire is copper, or wire is aluminum, or wire is gold, or silver, none of which are ferromagnetic. So just having a magnetic field there is not going to exert any force on it. But the electrons flowing through it, the current flowing through it, is a different story. This magnetic field is going to exert a force on the current flowing through this wire. Now, what is the strength of this magnetic field over here? These are a distance L. No, not L. L is something else. What am I? Not right. Okay, we'll call it D. They're a distance apart. Yeah, we can call it R. That'll be appropriate. There are meters apart. And no, that was not improper English. The magnetic field right here is going to be the magnetic field produced by current 1, mu sub naught over 2 pi times I1 divided by R. Look, they used a D in the book after all. I'm on page 571 if you want to follow along. Now that's the magnetic field right here. It's going that way, it's pointing into the board. Wait, why are they changing the subscript here? Okay, I see what they're saying. They're saying the force exerted here is the force exerted on wire 2. Call this wire 1, this is wire 2. The force exerted on wire 2 is equal to the current flowing through wire 2, which is I2, times the magnetic field produced by wire 1, B1, times the length of wire that's exposed to that field, L2, the length of wire 2 that's exposed to the field. Yeah. Well, we can replace B1 with this, and we get the force exerted on wire 2 by the magnetic, on the current in wire 2, by the magnetic field produced by wire 1 is now equal to mu sub naught over 2 pi times I1 over R times I2 times L2. That's the magnitude of the force exerted on this wire, on the current in this wire, by the magnetic field produced by the current in this wire. Who remembers the right-hand rule for the direction of a force exerted on a current? What's the direction of the force exerted on this current? Put your fingers in the direction and then turn them towards the... Yeah, and I've got this backwards, don't I? The direction of that magnetic field is into the board, not out of it. And now the direction of the force exerted, you point your fingers in the direction of the current, flip them in the direction of the field, and the thumb points in the direction of the force. So the force exerted here is so. Now, look at what happens, the force exerted on this one. The vector, here we've got the current going, make sure I'm doing the right-hand rule of thumb. The current is going this way. So the vector field for this wire is pointing out of the board here. and the current flowing in that wire is producing a force pointing this direction. Point your fingers in the direction of the current, bend them towards the direction of the field, thumb points in the direction of this force. So the force on wire 1 on the current in wire 1 by the magnetic field produced by the current in wire 2 is in the opposite direction. What's the magnitude of this one? The only thing that we would change would be the subscript here and here. And as long as you're talking about the same length of wire exposed to the same field, the same magnitude of field, both of these forces are equal and opposite, whether the currents are the same or not, because they don't depend on they depend on the product of the two currents. So even if the two currents are different currents, the two forces are going to be the same because both currents affect both forces. See that? F1 will be equal to F2 when you have two long parallel lines. If the currents are both flowing in the same direction, the forces are going to pull the two wires together. If one current is going one way and the other current is going another, then what happens? They go in opposite directions. Here we put I1 going this way, I2 going this way. What's the direction of the magnetic field produced by I1? Thumb down, so it's going into the board over here, out of the board over here. And that one, into the board out here, into the board over here, out of the board in here. Wow. Not going to leave that like that. There. Now, what's the force exerted on this wire by this magnetic field? I'm sorry, the force exerted on the current in this wire by this magnetic field. Current's in that direction, magnetic field is coming out of the board, the force is pushing this way. On this one, the force on the current in this wire by this magnetic field, come down, point your fingers out, your thumb is going that way. So the forces, again, are equal and opposite, but they're now pushing the two wires apart. Anybody have any questions about it, how this is all working? Or do you just want to discuss it? Because this is one of those times when if it's not clicking, if you're not wrapping your mind around what is acting on what, they're still both solved the same way. But, it's important to understand that the magnetic field is not being produced by the wire. The magnetic field is being produced by the electric current in the wire. And the magnetic field is not acting upon the wire. The magnetic field is acting upon the current in the wire. Okay? If this wire had no current flowing in it whatsoever, this magnetic field would not exert a force on it. Unless, like I said before, it's made out of some kind of ferromagnetic metal or conductor. All right, well, let's keep moving. Solenoids and electromagnets. Like I said a while ago, so far we've just been talking about long, straight wires. How many times do you work with long, straight wires? Let's talk now about solenoids. And boy, I don't know, I'm going to try to draw this. And we're all going to pretend that that's nice and smooth and uniform. Okay? All the spaces are the same, all the wires are the same size. You've got a current flowing in, and by Kirchhoff's current law, you've got the same current flowing out. What magnetic field is this wire producing right here? Right here. Current is going that way. So the magnetic field is going into the board here, through the middle of the loop, and back out of the board here, forming a little circle like that. If we draw this, we cut it in half and look at the cross section here. We've got a wire coming in here. Something like that. The magnetic field produced by that little wire is going like so. Same here. So I'm going to take this piece right here. I'm going to draw it bigger so we can see it better. Like that. Now, here the current is coming out of the board. And here, the current is going back into the board. So here, it's coming back out of the board again. Now that means that the magnetic field on this one is doing this. And the magnetic field here is doing the same thing. Now, let's talk about how these vectors sum together. You'll notice right here, this vector and this vector are equal and opposite. That means they cancel each other out. Here, this one has this component and this component. Same here, it has this component and this component. So, these two cancel each other out, and these two add together. And the same thing happens up here. So these two wires combine together to produce one magnetic field that looks like this. Everybody see how this works? All right. Now, let's come back over here and look at the bigger picture here. What we now have are magnetic field lines doing this. Right? What about here? Here, the current is going into the board. Not coming out. Well, what magnetic field does that produce? Thumb in the direction of the current, fingers in the direction of the magnetic field. Same thing is going on here. But on the inside, all of these magnetic fields are adding together. So what you end up with, try changing colors here. You end up with all of these vectors inside the coil are summing together and therefore increasing in magnitude. So you have lots and lots of high density, strong vectors inside the coil. And outside the coil, they spread out. So basically that solenoid becomes a bar magnet. Now, who remembers, does the magnetic field point toward the North Pole and away from the South Pole? Which means this would be the South, that would be the North. I hope I didn't get that backwards. Look it up and verify. Don't just take my word for it, because I'm not real good at memorizing arbitrary stuff. But, yeah, I think that's how it is. The North Pole, the magnetic fields point into the North Pole of the magnet and out of the South Pole of the magnet. Yeah. If I'm wrong, then it's just the opposite, but it's still true. The solenoid, the magnetic fields, based on this direction of positive current flow, produces those magnetic fields. It becomes one, that solenoid, that long coil of wires becomes a bar magnet, or the equivalent of a bar magnet. Does everyone see how that happens? How these vectors, all these little wires add together so that the magnetic field between them goes away and it combines to form one big magnetic field, and then they all add together on the inside to intensify, and they rarefy when they go out. All right, well, we've got one more subject I want to introduce today, and then we will call it a day. We're going to talk about Ampere's law. Oh, he has a grav over one of his E's. So we got two wires. and current flowing in that direction. They are now producing a magnetic field. Ampere's law states that if you integrate a closed path around these wires, but we're going to talk about adding little tiny sections of delta L in any arbitrary path around a surface. These wires, the current flowing in these wires is now producing some magnetic field. Now we know that because they're straight, I've drawn them long and straight, but they're round magnetic fields, but they don't have to be round, they don't have to be long and straight. They can be in any shape, size, color, it doesn't matter. They can be curved, straight, when you take this path of little tiny sections of delta L in any arbitrary path around these two current carrying wires, and you multiply each one of those little tiny delta L's times the parallel component of whatever magnetic field is being produced. Say that the magnetic field is pointing in this direction. Okay? The parallel part of this is going to be this component of the magnetic field, whereas the perpendicular is going to be this component. You see how that works? You've got a parallel component of the magnetic field that's parallel to the little tiny section of delta L, and you've got a perpendicular component of that magnetic field. If you multiply the tiny section delta L with the component of the magnetic field that is parallel to that little tiny section of line, and you sum those up all the way around a closed path, they will be equal to mu sub naught times the net enclosed current. Okay, times the net current passing through that closed path of integration. All right? What if one current was going one direction and the other current was going the other? What's the net current? Assuming they're equal and opposite, that would go to 0. And the sum of all of these little sections, these little parallel paths of magnetic field would sum to 0. Doesn't mean any one of them would actually be 0, but all of them together would completely cancel out. And you would end up with 0. In order to have a net magnetic field, you have to have some net current flowing. Okay? No, it's the net current that matters. That's all it's saying, is that there has to be some net current flowing through, where the net current is the sum of all of the currents flowing through that closed surface. All the net sum of all of the electrical currents flowing through the closed path, through that enclosed surface area. Oh, yeah. Yeah, you're not gonna. I'm not gonna give you a. I'm not gonna have you doing calculus on an exam. Okay. Don't panic. Okay. I'm just showing you this to give you the general understanding of how it works. Okay? We're not going to have to actually do calculus. You're not going to have to perform closed-loop integration. But, fortunately, because this is a generally true statement, we can often use very conveniently chosen paths to add up around that will give us some useful information. Look at here's one example. The field, the magnetic field, due to a long straight wire. Let's choose a complete path of integration. We've got a current flowing, I1, flowing in this direction. Now let's choose a circular path at a constant radius r around that wire. If we take and we multiply B parallel to that wire at all of the little delta L's going around it, can't even draw a sigma. That is a sigma. Thank you. Well, what is that going to sum to all the way around? What do all of the delta L's add up to when you go around a complete circle? 2 pi r. And the sum of all of the little pieces of magnetic field? That is the sum of the parallel magnetic fields times delta L's. But what is it equal to? According to Ampere's law, it's equal to the permittivity of free space, mu sub naught, times the total current enclosed. Do you recognize this equation now? B times 2 pi r equals mu sub naught over I, the total I1. Or B is equal to mu sub naught over 2 pi times I over R. Just like we'd already determined. We'll pick up here when we come back on Friday, and we'll use Ampere's law to quantify this mess of a magnetic field in this closed solenoid. That's not going to help us because this is no longer a long straight wire. Right? We looked at the individual little tiny pieces of it to see how they all add together to form this one big magnetic field. When we come back on Friday, we'll use Ampere's law to analyze this and to quantify how big that magnetic field is. Everybody sign in? Anybody have any more homework or any labs they want to turn in? Before anyone leaves, everyone wasn't here at the beginning, so I'm going to tell you all again. 15 March 2019. That's about 2.5 weeks, 3 weeks from now. It's the last day of classes before spring break. It's also the last day to turn in any late assignments, late homework, makeup exams, labs, whatever you want to turn in late, turn it in by then. Here's the deal. You turn it in by then, I will use my spring break to get it graded, and you will get credit for it. I'm not a hard nose. I bend over to try and give y'all as many points as I can. You turn something in after the 15th, I'm not going to refuse it. I will accept it. I will not even penalize you. I won't deduct points off of it for being late. I simply will not guarantee you that I'm going to get a chance to grade it. You turn it in after the 15th. If I can, I will get it graded and I will give you credit for it. And if I cannot, then you just don't get the points. And that they become zeros on your grades. So the 15th that's the due date. Make sure you get it turned in by then if you want to be assured of getting the credit. Thank you.